So welcome to Module 5, Part 1 live lecture. So this week we're going to continue talking about hypothesis testing. So we're not going to get away from it quite yet. Hopefully you didn't chuck your notes. Hopefully you didn't chuck any of your notes for this quarter because you'll need them by the end. But this week we are definitely going to be continuing off last week's lecture and last week's content. So we're going to do hypothesis testing using 2 samples. So how does that work? Well, this week we're going to increase to 2 samples to see if there's a significant difference between those 2 samples. So when would we use this? Why is this important? Why do we need to look at 2 different samples and compare if there's a difference between them? I should say a significant difference. Well, here's some ideas, and I did throw some out there in the course announcements and everything, but if you have a drug company and you want to test the effectiveness of a drug, you have to have a study done, and where basically you have 2 samples, and usually you compare it to a placebo where they're not taking the drug but they think they are, compared with people that are actually taking the drug. And you have to compare the 2 to actually see if they work. And that's the idea. This is where this would come into play, if you've ever seen that before type of idea. Same thing with like weight loss. If you're comparing 2 types of weight loss, or if you want to compare how effective like a weight loss, like low-fat diet or keto diet or anything like that, and you're comparing it with just a normal diet, you know, type of idea, is there a significant weight loss? And that's how they actually figure out if there is or if there isn't. Scientifically, you have to do these studies to be able to say certain statements from the FDA, right? They go through and they look at the studies and go, okay, we agree that that drug does actually make a difference. So you can actually make that statement. Otherwise, you can get fined quite badly. Yeah, not a good thing to lie to the consumer. Anyways, so when we're talking about these 2 different samples, there's 2 types of samples. There's independent and there's dependent samples. Now, let's start with talking about independent samples. Independent samples are if the sample values from one population are not related to or somehow naturally paired or matched with the sample values from other populations. So basically what that means is independent is that you're not linking the 2 ideas. They're basically 2 different groups. So for example, if you're trying to do like a weight loss on 2 different groups of people, maybe they're on a low-fat diet and maybe they're on a high-fat diet, and you're trying to compare the difference. These are independent because they're different different ideas or different populations, and they're not matched. Okay, they're not matching them. Whereas if you have a dependent to dependent samples, okay, these are going to be thought of as matched pairs, and essentially what's happening is that they're going to be matched or they're going to be linked. So you're going to have a person and a person linked, kind of going together. So based on some relationship. So an example would be a group of subjects were put on a weight loss drug and then taken off the pill. And their before and after weight loss were recorded. So you're coming from the same population, right? You have your people and they're taking the drug, and then they go off the drug. Same people, same group of people, just different results. What happens after they go off the drug? So those are matched because you're doing like a before and an after type of thing. A good rule of thumb, if you're not quite sure the difference between independent and dependent, is if you have 2 samples, 2 sample sizes, which are different sizes, they're usually independent because that means they can't be matched up. So if like I have 25 students here and 30 students here in this group, they can't be matched up, right? There's going to be 5 extra students that don't have anybody to match up with, so they're independent, okay? They're not the same. Whereas if the sample size is the same, it's more likely that they're dependent. You just have to see if they're matched, or you can match up those ideas. And this week, in this first lesson, we're just going to be talking about independent samples, and I'll try to go through that idea a little bit more. On Wednesday, I did move the live lecture from Tuesday to Wednesday this week, simply because Halloween's on Tuesday, in case anybody needed to trick or treat or anything. We're just going to move that to Wednesday at 5:30, same time, just on Wednesday. And we'll be talking about dependent examples and how to do hypothesis testing on dependent samples, okay? So we do need to talk about our favorite thing. You know I push this a lot in the class, but variables. Now, these variables should all be familiar because we've talked about them all before. The only thing that's different here is that you see you've got numbers underneath those variables. And the idea is that you're just telling them what group you're coming from. Are you coming from population 1 or are you coming from population 2? So if you look here, population 1, we have, our population mean mu, our population standard deviation sigma, population proportion p, our sample size n, our sample mean x bar, our sample standard deviation s, and our sample proportion p hat, a little hat on it. We haven't talked that much about our proportions p and p hat, but all the rest should be very, very familiar to you at this point. Notice that since they all come from population 1, we just have a little 1. So this would be mu1, sigma 1, p1, n1, x bar 1s, s1, p hat 1. Just throw 1 after it, knowing that it's coming from the first group. And you can see the same thing for population 2. We've got those same variables. The only difference is they've got a 2 instead of a 1, meaning they're coming from population 2. So don't get hung up on those numbers. They just tell you what group they're coming from. That's all they're saying there. Okay? And literally you just read them like mu2, sigma 2, p2, n2. Just read it like straight like you would, even though they're a little smaller and off to the right. Okay. So hopefully those look really familiar to you. Just the numbers are new there. Okay, so let's talk about inference about 2 means. So specifically, we're going to be talking about population means, our mu. We love our mu. We love talking about our population mean, average, based on 2 populations. Now, we're going to be talking about independent samples, as I mentioned earlier. So these 2 are 2 groups that don't come from the same population, and we're going to look how they interact. So, note, we are going to approach these problems as if sigma 1 and sigma 2 are unknown. So if you remember from last week and the week before even, we talked about the idea that if we don't know our population standard deviation, which is our sigma, which variable do we have to use? If we don't know sigma, we have to use our T. Exactly. We've got to use our T statistic if we don't know our population standard deviation, which is our sigma. So we're going to keep going with that idea. We're going to use our T for test statistic. Now, so we're going to be using those same ideas we did last week, the T distribution, the T inverse, those PDFs that I handed out last week. We can use those too. No problem. The formula for the test statistic is going to be a little different here, okay? So this looks really nasty. I'm going to be honest with you. You want to be very, very careful typing this in, but don't worry. We will do, I have 3 practice problems if we can get through it to work through this idea to make sure that you know how to type that into Excel. The key thing here is that this parenthesis here, mu1 minus mu2, that's actually going to be a 0 value. So when we type this in, we can actually just type in the mean from the first group minus the mean, the sample mean of the second group, divided by the square root of S1 squared divided by N1 plus S2 squared divided by N2. So on the top, we're subtracting the sample means from the two groups. And then on the bottom, we're taking the square root of your sample standard deviation squared divided by our sample size from the first group. And then we're adding the sample standard deviation squared divided by the sample size of your second group. And we'll walk through that. I'm going to tell you reference cells are going to be amazing to use in this example. So that's going to be super helpful here. Now, degrees of freedom are going to be a little bit different. So far, we've done it so that the degrees of freedom are your sample size, is your sample size minus 1, n minus 1. Well, the problem here is we have two sample sizes, n1 and n2. So what we're going to do is we're actually going to calculate the degrees of freedom for both. So just take each sample size, subtract 1, and then we're going to pick whichever value is smaller. So if the first group is smaller, we'll pick that one. The second group is smaller, we'll pick that one. Okay, so just pick either one. So same idea, subtracting 1 to get the degrees of freedom, but this time we have to do it twice and then pick the smallest. Okay. We're still going to be using the same steps as before. So steps 1 through 3, we got to come up with that hypothesis. All right, the null hypothesis and the alternative hypothesis. We also need to figure out our alpha, our level of significance. We also want to go ahead and calculate the t-statistic and then use that value to do either the critical value or the p-value. So either one. So hopefully last week when you did that homework assignment, you looked back on it and you found that you came to that same conclusion, whether you did the critical value or the p-value. Did everybody find that last week? They're doing deliverable 4. Yes? Okay, perfect. Yes, so always coming to that same conclusion, whether we reject the null hypothesis or fail to reject the null hypothesis. And then, of course, we have to restate that in non-technical terms, aka we need to translate it for everyday Americans, right? Okay, so that we all understand what we're talking about. Either there is sufficient evidence or there's not sufficient evidence to support your claim. So the null hypothesis is going to look a little bit different this week. The null hypothesis is still going to be HO, okay? But your statement here is not going to contain any numbers. That's different. We usually have numbers. Instead, the null hypothesis is going to be that the sample means are equal. That means that there's no difference between those two samples. So when we're comparing those two samples, there's no difference here between them. So we would say the sample mean, population means of both groups are equal. And that's exactly what we're saying here. Population mean of group 1 is equal to population mean of group 2. So mu1 equals mu2. Now the alternative hypothesis, you can still have H1 or HA, but remember, we're not going to be having any numbers. Instead, depending on what your claim is, whether it's less than, greater than, or not equal to, you're going to have different results. So for example, if your first group is supposed to be lower than your second group, you would be using this left-tailed hypothesis, alternative hypothesis. If you're saying that your population mean of your first group is greater than your second group, you would be using this right-tailed alternative hypothesis. And then last but not least, if you're saying your two means are not equal, so it's either larger or smaller, we're not really going to be using this one much, but I thought I'd mention it. This would be a two-tailed test, so on both sides. We haven't really worked with that guy very much. So just keep in mind, you're not going to have numbers in the null hypothesis or the alternative. You're just going to be talking about comparing the two population means here. Any questions yet? Are you just waiting to see an example to see how it all comes together? Probably. Okay, let's jump into an example then. And then as we go, we can hopefully clear up any questions that pop up. So I got this information from the book, and basically it says it's about cola weights and volumes. So the weights of the contents of cans of Diet Coke are given. Okay, so this is our Diet Coke up here. Use a highlighter. Here's Diet Coke, and here's all the information for Diet Coke. So since this is the first group, we're going to go ahead and label that N1. That should be X bar 1. Sorry for that. And then this should be S1. So just to make sure we establish that. So your sample size is 36 for Diet Coke. Your average weight for that sample is 0.784 pounds. And your sample standard deviation is 0.00439 pounds. Now, for regular Coke, they went through and they did another sample. And you can see here that regular Coke is going to be our second group. So these values are going to be labeled with a 2. So this is going to be N2. Okay, well, you're not going to want... Oh, no! No, stop. Sorry, PowerPoint is not agreeing with me right now. Okay. There we go. Okay. So this should be N2 is 35 or 36. So we have the same sample size, but these are from different populations. Notice we're talking about Diet Coke and regular Coke. These are two different ideas. This is why they're independent of one another. They come from two different populations. They're not the same. So these are independent. Our sample mean for regular Coke is 0.81 pounds, so a little heavier than the Diet Coke. And our sample standard deviation is 0.00751 pounds. Now, we have all the information given to us. We don't actually need to calculate anything, and you might be happy because in your homework, you're going to have all that information given to you as well. So you don't really need to calculate anything like we've done in the past couple examples. Yay! Just go through the hypothesis testing. So use a 0.05 significance level to test the claim. So here's what they're claiming, that the contents of cans of Diet Coke have weights with a mean that is less than the mean for regular Coke. So here we're comparing Diet Coke is our first group and regular Coke is our second. If you want to, you can label that group 1 and regular Coke is going to be group 2, just to help divide up and understand those concepts. So the first thing we need to do, what we did last time, is we need to come up with our null hypothesis and our alternative hypothesis. So our null hypothesis is always going to be the same, that in fact the means, the population means of the two groups, mu1 and mu2, are actually equal. What do you think the inequality is going to be for our alternative hypothesis? You always want to put your mu1 first and mu2 second. Less than? Yes, absolutely. And the reason for that is they literally say less than. Smaller, less than, anything like that means less than symbol. So very good. So we've come up with steps 1 through 3. Woohoo! Knocked those out. So we know our claim is that Diet Coke weighs less than the regular Coke. That's essentially what they're saying here. So we need to test that claim. Let's find out if Diet Coke and regular Coke have different weights. Okay, sounds good. So step 4, same steps as before. Like we're not doing anything excitingly new, really, but our significance level is 0.05, so alpha equals 0.05. We've talked about alpha and our significance level. It's right here. 0.05 is our significance level. So number 5 is kind of the new step. So remember, we're not using sigma here, so we need to use S, which is our sample standard deviation, which means that our variable, our test statistic needs to be T. I knew you all said that out loud, right? Okay, great. So if we remember, I have my little cheat sheet here so I don't forget anything. So T equals x1 bar minus x2 bar. Now we don't write in our mu1 minus mu2 because those are assumed to be 0 because we assume that they are equal right here. So that's why we don't write those in. So then we're going to divide it by the square root of s1 squared over n1 plus s2 squared over n2. So instead of actually writing in all of this information, because quite frankly it's silly to keep rewriting it, we're going to go ahead and type in all the information in Excel and just grab this and be able to use reference cells to grab the information. So let's start with Diet Coke. Diet Coke information. I'm going to go ahead and write all my information. So N1, which is our sample size, is 36. X bar 1 is going to be 0.78479, and we don't want to round until the very end. S1 is 0.00439. Great. Now let's go ahead and do our regular Coke, which is group 2. So this is N2, it's 36. X bar 2 is going to be 0.81682. Double check that I typed that incorrectly. And then S2 is going to be 0.00751. Double check that you typed that all incorrectly. You could also, if you wanted to, you could put that over here. Oops. So that you have them all on the same level, if that helps. You don't have to, and then you can do your calculations down below. So we need to calculate our test statistic first. Statistic, yay. Let's see, let's make that a bit bigger. So remember, equals. Now we're going to go ahead and on top, in parentheses, the top is in parentheses, we're going to take X bar 1, which if we look over here is 0.78479. We're going to subtract X bar 2. So we grab that. We have closed those parentheses because that's the top of the fraction. Okay, so we've subtracted those on top first. Now we're going to divide. Now here is where we need to use that square root. So SQRT is going to give our square root parentheses. Now what you're going to do is you're going to take S1 squared. So here's S1. I'm going to grab it and I'm going to square it. To square it, you need to hit the up arrow. The up arrow is Shift 6. The up arrow is Shift 6, and then put in 2. So what's happening there is we are squaring my S1 value, and I'm going to divide that by N1. So I'm just selecting my appropriate boxes. Do you see how setting this up, you can just go grab the items and then it's color coded so you can see where it's referencing. So if you do make an error, it's much easier to see if maybe you typed it in incorrectly. So that's why I'm using those reference cells. Now, we have to do the same thing to S2 squared. So we're going to add S2 squared. So I'm going to grab S2 and I'm going to square it. So I'm going to raise it to the second power. Raise it to the second power. And then divide by N2, which is 36. Okay. Now you can close the parentheses because we have everything inside those parentheses. We have everything selected. We give it a glance over. We're subtracting the means on top. And on the bottom square root, we've squared our sample standard deviation, divided it by our sample size, added it again to the other sample standard deviation squared, divided by our sample size. Hit enter, and you should get a really terrible number, -22. That seems humongous. Okay, well, we got, our T was -22.0923. That is a humongous test statistic. Normally you don't get that big of a test statistic, but let's just go along. Did everybody else get that? Was everybody else able to calculate that? I know that gets kind of, okay, great. Okay. Wonderful. Yeah, it's so important to practice being able to get the Excel, be able to use Excel. Because if we don't do that, we're not sure we're typing it incorrectly. So this is a huge number. This is our test statistic. Let's write that. Yes, I can. There you go. The next thing we're going to do is we're going to do our 2 steps. Where you can either do the critical value method or the p-value. I, of course, am going to show you both. I believe in the document they tell you to do it one way or the other. You got it, Lori. But we'll talk about that when we get to the homework at the end. So let's just go through both because it's good practice. We like to make sure we're practicing those ideas. It's my sound effects for stats. Okay, so this is 6A. This is 6B. We're going to go ahead and show the critical value method. And we're going to do the p-value as well. So for the critical value, since this is a left-tailed test, and we know that because we look at the alternative hypothesis, it is less than left-tailed one side. Boom. So we're going to go ahead and you can use that PDF to identify, oh, it's left-tailed. That means that the critical value to calculate it, we're going to go ahead and use the T dot inverse. And we're going to plop in alpha, comma, degrees of freedom, which in our case, alpha is going to be 0.05. And the degrees of freedom, remember this was a little different than we did last time. Our degrees of freedom are n-1, right? Well, here we have 2 different n's. Actually, they're the same value, so it doesn't matter which one you're going to pick, right? 36 minus 1 is the same as 36 minus 1. So our degrees of freedom are 35. Yep, there you go. Boom. Now, if they were different, just make sure you're picking the smaller number. Just pick the smaller number. Okay, so let's calculate our critical value. Sorry, I'm really into sound effects today, apparently. So critical value equals T dot inverse probability 0.05, comma 35. Hit that enter, and it looks like our critical value is negative CV equals negative 1.68957. Okay. Now I'm going to show you the long way of how to interpret that. You can always use our shortcut, which is that PDF, to help interpret in case you're struggling with this idea. So just as a reminder, we talked about this last week, but when you have your t-distribution, yay! Now it is left-tailed, so we're going to go over here. Remember, this is 0, the mean is 0. Negative 1.68957 would be on over here. Negative 1.68957. This would be your critical value, so anything to the left or lower than that number is going to be in your rejection region. Wow, my spelling is awesome today. It's supposed to be a G. Region, okay. Rejection region in there. So if your test statistic falls into that region, that means you got to do some rejecting. Okay, so does our test statistic fall into the rejection region? I think this one's pretty obvious, right, guys? Is negative 22 less than our critical value? Heck yeah, it is. So we would say that our test statistic T is less than our critical value, meaning that we would reject the null hypothesis. This is actually step 7, in case you're taking note. So our T, negative 22.09, is less than negative 1.69. I mean, it's not even close, right? You're like, that's way over in the rejection field. Like, throw that out, Alicia. It's way over there. So we're going to reject the null hypothesis, which, if we want to pull up our little summary sheet of what happens, let's go ahead and do that. Oh no. So, look at all those answers in there, guys. You just pull that up, right? Just pull up those answers. Just want to make sure I pull these up so we know we're using them still. Okay. So here's what I was talking about. You're trying to come up with your critical values, left-tailed T dot inverse alpha and degrees of freedom. Same thing we did last week. And then our hypothesis test, since we have a less than, since our test statistic is less than the critical, we reject HO and evidence supports claim. So we conclude by saying, this is the part that I hate writing out. I'm sure you guys do too. There is sufficient evidence to support the claim that, and what's our claim? Let's go back. Claim that the contents, okay, I'm not going to actually write this all out because it's right up here, but the contents of cans of Diet Coke have weights with a mean that is less than the mean of regular Coke, aka Diet Coke weighs less. We learned something today, guys. I don't know how useful that information is, But hey, you can go up and tell your friends. A little nugget of information. Diet Coke weighs less than regular Coke. Okay. So that was the first way, using the critical value method, but we also need to use that p-value. So let's go ahead and wander over to p-value land and do some calculations. So we're trying to find the probability of getting our test statistic. And let me tell you that it's going to be pretty low. So t.dist to find the probability. And we're going to put in our test statistic, comma, degrees of freedom, comma, true. So in here, we're going to be t.dist. And our test statistic is that negative 22.0923. Degrees of freedom, we already said, was 35. And of course, true. That just tells you that it's cumulative and you keep on adding up, which for continuous variables, that's always true. Okay, so we're coming up with our p-value. T.dist. And we can use this because it is left-tailed as well. We just plop it right in. We're going to want to grab our test statistic. Let's not rewrite that because we don't want to mess it up somehow. So we're just going to grab that using a reference cell. Comma, degrees of freedom are 35. And true. Okay. Boom. Now, if you notice there's that e in there, 1.93376e to the negative 22. Remember that means this is scientific notation. And this is scientific notation meaning that you're going to have 22 zeros in front of the 1. So this is like 0.000000. Imagine there's 22 zeros there. And then you have 19337. So for all intensive purposes, that's 0, okay? I mean, you're not going to write this all out, right? 0.000, we could write it out if we want to. 22 zeros. 1.933 times 10 to the negative 22nd. Okay. So whenever you have an e in there, that just means it's scientific notation. So if there's a negative number after it, that's how many zeros go in front. So this means this would be 0.000. Imagine 22 zeros. 1933, so on. 22 zeros. Okay. We don't want to write all that out. So it's a really, 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 really small number. So remember when you're doing the p-value, so this is not very likely to happen, meaning that our p-value is less than our alpha, right? This value right here is less than our alpha. Our alpha is 0.05. So if that's true, remember our Snoop Dogg reference. If the p is low, the ho's got to go. So we come to the same conclusion. We reject the null hypothesis, and we conclude that there is sufficient evidence to support the claim. Oh, thank you. I feel like I'm going to offend somebody, and I feel really bad because I don't want to offend anybody about that, but hopefully it gives you a little bit of a chuckle. Don't take it too seriously. Just trying to come up with ways for you guys to remember that. So any questions on what we did here? Does it feel a lot like last week? Like it doesn't feel like too much more? What are we thinking? How are we feeling? Whenever it's like, whenever you have this E, can't do that. Oh no. There we go. Whenever you have that E in there, that signifies scientific notation. We would really write this out as, let me write it out here. That is not my pen. it would be 1.933 times 10 to the negative 22nd. There's too many zeros. Excel can't handle that, so it throws an E. So it's 1.933 exponent of negative 22. So that's scientific notation. You won't get that in your homework. This was just like an extreme example because our test statistic is so far to the left. Yep, we did have that before, Lori. I love that you remembered that. Unfortunately, to format the cells, you would need to literally you'd right click and then format cells. Let's see if this will even work. Let's try it for fun. And then your number, you'd have to do decimal places, like 22. Yep, you can format it to 30. Boom. There you go. That's what 22 zeros looks like. Yay! So you could technically do that if you wanted to. You could format. Yeah. Just, I mean, you know that number is like ridiculously small. So automatically reject the null hypothesis, move on with life. Okay, great questions. Love that you guys are feeling this. Feels like last week. Not too bad. So let's do one more example because I think that's all we really need to do. So researchers from the University of British Columbia conducted trials to investigate the effect of color on creativity. Subjects with a red background were asked to think of creative uses for a brick. Other subjects with a blue background were given the same task. So essentially, if you ever get into psychology or sociology or anything, this really plays a big role. Is this more effective than another? Is having a red background more effective than a blue background? For you business people, which most of you are, this is like saying, what color should I use for brand loyalty? That sort of thing. Like they do studies on it, right? To make sure that colors actually trigger stuff. So anyways. Responses were scored by a panel of judges, and the results from scores of creativity are given below. Higher scores correspond to more creativity. The researchers make the claim, so here's our claim, that blue enhances performance on a creative task. So in other words, blue's going to be more creative. Blue's going to give you those higher scores, more creative, higher scores, as was in the sentence before. So blue enhances the performance. Blue gets you higher scores. Fun fact. Let's see if this is actually true. Okay. We're using a different significance level. We're changing it up. We're going to do 0.01 because why not? So again, we have two groups. These are two different sets of people. Okay. And one's has a red background and one has a blue background. You can't really use the same people because obviously they've had time to look at the brick and think about it, so you can't use the same people. So they're different different populations, different groups of people doing each one. So you have the red group and you have the blue group. So red group is going to be group 1. So we're going to label it N1, X bar 1, S1. Again, we don't know the population standard deviation, so we're going to use our T statistic. I'm jumping ahead. Okay, not quite yet. Blue background is going to be our second group, so we're just going to label those 2. Boom, we've got all our information for group 1. And in fact, you could label it group 1, group 2. That's supposed to be a G1, G2, group 2, just to break it apart. So the first thing that we want to do, steps 1 through 3, those are my favorite steps. The null hypothesis. So what's the null hypothesis here? Anybody want to take a stab at that? Exactly, great. The mu's are equal. Mu1 equals mu2. We're not working with any numbers here. We're just saying there's no difference between these two things. So that's how we know. Oh, quick note. Another way to know that these are independent groups is notice that the sample sizes are different. That automatically means it's independent because they're not matched. Okay, your alternative hypothesis. What do you guys think? Be careful here because mu1 is our red group and mu2 is our blue group. So if you need to just think of this for a second, you can even write down here, that's our red and that's our blue. So what type of inequality? Which mean is supposed to be larger? If we go back to our claim, the claim is that blue enhances performance, meaning that higher scores correspond to more creativity. So that means that blue needs to have that higher value. So we are going to do less than, because blue needs to be greater than. Sometimes it helps when we like tell which group is which, and just make sure it's eating the larger group. That's how I think of inequalities. It's like a mouse. I want to eat the bigger one. So blue has to be larger than red, which means that red has to be smaller than blue. Does that make sense? So blue is more creative. That's the claim. Blue is more creative, meaning it has higher. So this number over here that corresponds to blue should be bigger than red. So less than indicates that red is going to be smaller than blue. Does that make more sense? Okay. I'm getting squeaky over here. So for, my chair is squeaking up a storm. Our alpha has changed. It's 0.01. Let's see. 5, we need to go ahead and do our test statistic. Okay, and just as a reminder, t equals x1 bar minus x2 bar all over the square root of s1 squared over n1 plus s2 squared over n2. Okay. Now we're going to go ahead and fly on over to our wonderful Excel document. I'm just going to go ahead and grab a new sheet so that I can do the work over here. So we're going to do the same thing where we're going to do our information for our groups. So this one I'm going to make my red background. So N1 is going to give me 35. X bar 1 is going to give me 3.39. S. Let me label them appropriately so I know what I'm grabbing. 0.97. Now let's do our blue group over here. Blue group, the more creative, N2 is going to be 36. So 36 people looked at this brick and came up with different creative ways to use it. I'm not good with that. So X bar 2 is 3.97 and S2 is going to be 0.63. Okay. So we plugged in all of our information to Excel so we can use those reference cells to make our life a little bit easier. So down below, we're going to go ahead and come up with our test statistic. Okay, so equals, now remember the top needs to be in parentheses and we're subtracting our sample mean. So sample mean X bar 1 minus X bar 2. Close those parentheses. Okay, going to divide by the square root SQRT, parenthesis. Now remember, we need to take S1 squared. So here's S1, shift 6. 2 is going to give you that square that you're looking for, divided by N1 plus We're going to take S2, we're going to square that, so shift 6, 2, divide that by N2, close parenthesis. So double check that we typed it all in correctly. Then you're going to hit enter. This seems like a much more reasonable test statistic. Usually we don't get things like -22. It doesn't normally happen that way. So our test statistic is going to be -2.97895. Did we all get that? Any questions on that one? Maybe I shouldn't ask 5 questions all in one. Go ahead and double check that you type that in, selecting the right ones. So make sure your X bars are on top, and you've squared each one, divided by the sample size. Okay, so once we have this test statistic, we're going to go ahead and do our 2 different methods, same thing we've done before, the critical value and the p-value, and then come to our conclusion. So did you get it? Did you find that error, Lori? Did we work through that? Okay. Yeah, but if you have different cells, it's not going to match up exactly the same, but just keep looking at it. Make sure that you're grabbing your labels using that formula down here. Yeah. Okay, so let's go ahead and do our critical value over here. So we like to label that 6A. That's step 6A. So critical value, you're going to go ahead and do your T dot inverse. This is alpha and degrees of freedom. Now, what type of test is this? Is it left, right, two-tailed? It is left, so that's why we can use this method. I feel like I should switch it up one of these days. So alpha this time is actually 0.01, so we're switching it up. Now, what do you guys think the degrees of freedom is going to be? This one's going to be a little bit different than we're used to. Yes, it is going to be 34. So remember, you're picking your smaller sample size. So here, the smaller sample size is 35. Subtract 1 off of that size, and that'll get you your degrees of freedom. So here would be 34. Okay, so let's go ahead and plug it in and see what we get for our critical value. See if we get anything exciting. So this will be our critical value equals T dot inverse 0.01, comma 34, close parentheses. It looks like our critical value is negative 2.44115. I will tell you on your homework, your critical value and your test statistic are going to be really, really close. So be careful with that. Don't round too much. Just a word to the wise. Negative 2.44115. Oh, I forgot to write my test statistic over here. So T equals negative 2.97895. Okay. So what we need to do is we need to draw our little handy dandy T distribution. There's 0 chilling out over here. Now the critical value is going to be at negative 2.44. That's what I'm going to round it to. Anything smaller than that is going to be in that rejection region. Reject. Okay, rejection region right in there. Now, we need to compare our test statistic to see which one is smaller. So our critical value is negative 2.44, and our test statistic t is negative 2.97. Now remember, the larger negative is actually smaller. So the larger negative is farther to the left. So it'd be in that rejection region. So which one is larger, the CV or the test statistic? Our t value is going to be farther to the left. So this is going to be, it's going to be like negative 2.97, chilling in that rejection region. So this is smaller. So yeah, so t is less than our critical value, meaning that it falls into the rejection region. You can also use that PDF to help identify which one, how you should conclude, which means we reject the null. I feel like I haven't done any examples where we do not reject the null. That's a bad on me. I should really do some. I bet you the next example that I'm skipping has it where it does not fall in the rejection region. Anyway, so when we reject the null hypothesis, we conclude that there is sufficient evidence to support the claim that, and then we do the claim. Blue enhances performance on a creative task. Yay! So if you want to be more creative, just put blue out there. I've got a blue study. Maybe that'll make me more creative. Who knows? Anyways, so, we have to do the other 6B, right? We almost forgot about it. Oh no! So 6B, don't forget about your p-value. We can do that real quick. That's not a problem. So we're going to do that t.dist. Since it is left tail, we're going to go ahead and just plug in our test statistic. And we're going to go ahead and do some degrees of freedom. And true, like we normally do. So t.dist. And our test statistic is negative 2.97. Obviously, we'll just use the cell reference so we don't have to rewrite it all. We've already told us the degrees of freedom is 34. And this is true. So let's plug it in. P-value, the probability of getting that test statistic. T.dist. And we grab our test statistic since we don't want to rewrite it, comma 34, true. It's really about being lazy using that cell reference. It makes our lives easier, so why not use it? So hit enter. So the p-value is going to be 0.00265. So this one, we don't have to worry about formatting the cell or anything to make it larger, so we can actually see that value at all. So equals 0.00265. So we need to compare that to our alpha. Now, this is our p-value, right? Okay. Sometimes it helps when you line them up. So our alpha is 0.01. Sometimes when you line up those digits, it can help. So they both have zeros for the first one, but if you notice in their second digit, in their 100th place, alpha is going to win out, right? It has a 1, which is larger than a 0, meaning that alpha is larger. So P is less than alpha. So P is low. The ho's got to go, so you make that same conclusion where we reject the null hypothesis by null, and we support the claim that blue enhances performance on a creative task. Yay! Any questions on this one? Did I go too fast on any part? Feeling pretty familiar? The only thing is that I can see people maybe, if you don't have things labeled correctly, it's easy to switch things around. So you want to be very careful about labeling items, and then using this formula here, be very careful of that square and the square root. That'll get you every time if we don't do that. Any questions on those? Otherwise, I'll jump to the homework. Okay, if you think of anything, just let me know. Okay. It feels good. It feels like you guys are good. Is that just me pretending? Crossing my fingers, hoping? Please be good. Hopefully it just feels a lot like last week, just a little bit different. Okay, so there are two examples. One is for an independent sample and the other is for dependent. Remember, we have not discussed dependent yet. We only talked about independent. So you're going to go ahead and demonstrate how to work through these ideas. Oh, real quick. So this is deliverable 5. There's no Excel sheet given to you, but you do need to go ahead and make sure you have an Excel sheet with your steps on it included when you submit it with your Word document. Every single week should have an Excel document attached to show your work, okay? Just wanted to be clear. So yeah, just like a new one like this, and then you just put in your information and do the calculations. So, independent sample. So one of our researches, which is to determine whether people with high blood pressure can lower their systolic, oh my God, so not into medical assisting, their blood pressure by taking a new drug they've developed. So the sample data is shown below, where X1 bar represents the mean blood pressure of the first group, treatment group. Thanks, Laura. Just laugh at me, it's okay. X2 bar represents the mean of the control group. So you have two groups here. One's the treatment group, one's the control group. So they do this all the time when they're testing drugs, right? Obviously, they're not the same. Otherwise, they could get different results. So different groups, independent of one another. The treatment group is over here. This is the treatment group's information. N1 is 80, X1 bar is 186.7, and S1 is 38.5. Whereas the control group is going to be the second group. They did not take the drug. 70 is their sample size. 201.9 is their sample mean. And 39.8 is their sample standard deviation. So those are the two groups and the two information. You need to go ahead and use the significance level of 0.01 and the critical value method. Let me just double check. Yeah, so in this one, this is a little different than we've been doing. You only want to use the critical value method for that independent sample. You don't have to do the p-value. If you would like to do the p-value to make sure that you did it correctly, feel free. You don't have to include that though, or don't include, well, doesn't matter. Don't include it because the graders might be like, why did you do both? I don't know. But you can do it if it helps you to reassure yourself that you did it correctly. Okay, so we're testing the claim that the drug reduces the blood pressure. So the drug, which is the treatment group, should have a lower blood pressure than the control group we have over here. Okay, so what's that mean? Yes, Lori. Okay. Oh, and you do not know the population standard deviation, so you got to use your T, blah, blah, blah. So number 1, write the hypotheses in symbolic form. Null hypothesis, alternative hypothesis, determine if it's left-tailed, right-tailed, or two-tailed, and explain why. Make sure you have those explanations in there. You know the drill by now. 2, calculate the critical value and the test statistic. We usually do the test statistic first and then the critical value. It doesn't really matter. Show your work, explain how you came up with that. And then 3, make a decision about the null hypothesis and explain your reasoning. So do we reject the null hypothesis, or do we do not reject the null hypothesis. And then make sure you put that claim back into non-technical terms. So that's where there is sufficient evidence or there is not sufficient evidence. And then you put the claim. To support the claim that, blah, blah, blah. So right now you can only do the first three. We're going to get to the second one, dependent samples, on Wednesday when we go through that. So knock out the first assignment, and then when you come back on Wednesday, you'll be able to hopefully knock out the second one. Sound good? Hopefully that sounds good. I was telling the lovely ladies here earlier that if you wanted to, you could actually start on deliverable 7. So I just wanted to show you this real quick. You don't have to. Did you guys like my little picture up here? Somebody cross-stitched this because they have way too much time on their hands. So deliverable 7. Basically, you're going to be doing a PowerPoint, but you have like a Word document that you can work through the questions before you transfer it to a PowerPoint. And you'll probably be able to answer some of these questions right off the bat. And there's also an Excel sheet right here. So if you wanted to, you could start working on deliverable 7 just to get a head start. If you don't have the time, don't worry about it. But you can see there's a spreadsheet that's given over here, actually. And then you'll see, like, introduce your scenario and data set, provide a brief overview of the scenario, classify your variables. So this should all look really familiar. Calculate the measures of, what are the measures of center and why are they important? Calculate them. And it's just really a summary of everything we've talked about. So a lot of the stuff you've already got. If you want to start working on that, we'll talk about more of this when it gets towards week 7 though. But just if you wanted to, you can always get started on that. Just throwing that out there. Any other questions about anything that's due? Any work or anything? Otherwise, you guys are free to go. I appreciate you guys coming. And hopefully I'll see you on Wednesday at 5:30. Bye, everyone.